Assalamu alaikum. This is Dr. Osman Alauddin, and I welcome you all in week 2 lectures of internal combustion engines ME 215. So these are the learning outcomes of today's lecture. In today's lecture, we will start the lecture with discussing with by discussing some applications of internal combustion engines and external combustion engines. Then we will discuss the two-stroke engines, comparison between four-stroke and two-stroke engines. We will also do uh, we will also watch a video to show a comparison between four-stroke and two-stroke engine. And then at the end of the lecture, I think I forgot to mention a point here that we will also discuss some few engine performance parameters. So in the PDF slides, I will add this point. So these are the learning outcomes of today's lecture. So if you remember, if you recall that in week 1 lecture, we started the studying the course of internal combustion engine with the definition of engines and heat engines. We discussed then the comparison of internal combustion engines and external combustion engines, and then we discussed about the four-stroke spark ignition engines and four-stroke compression ignition engines. We also discussed some basic components of an engine, a few widely used nomenclature of the engine, and then we discussed everything. We revised everything like watching few interactive videos. So where we learned all these things by watching the working of some real engines or some real or the models of the engines. So let's discuss a few applications of internal combustion engines and external combustion engines. So this chart shows a summary of different applications of the both internal combustion and external combustion engines. It's so I think we do not need to spend a lot of time on this slide, as you can go through this table, and this thing may be asked in the exams or in the practical viva, that please discuss few applications of the internal combustion engines or external combustion engines. Now let's discuss two-stroke engines. If you recall, students, if you recall, we also discussed this thing in the course of thermodynamics. If you recall that in four-stroke engines, we have like the first, let's suppose we have the compression stroke. So in the compression stroke, intake and exhaust valves are closed. Piston moves from bottom dead center to top dead center, and like we have, the pressure will increase and volume will decrease. So this is the compression stroke, and during the compression stroke, intake and exhaust valves are closed. So when piston reaches the top dead center, the spark plug gives the spark, ignition takes place, and the exhaust gases are formed. Now these exhaust gases are push the piston downward, so the piston will go downward from top dead center to bottom dead center. Volume will increase and pressure will decrease. So this is the power stroke or the expansion stroke. During the expansion stroke, forces are exerted on the piston. Piston is attached to the crankshaft with the help of connecting rod, and then this force is transmitted to the crankshaft, and the crankshaft rotates and the vehicle moves. So these are the two key events, two processes. Then the cylinder will be filled with the exhaust gases. Piston will again go from bottom dead center to top dead center, but in this process the exhaust valve will be opened, and all the exhaust gases will go out of the cylinder. And when we reaches to the top dead center, piston will again go back to the bottom dead center, but during this process the exhaust valve will be closed, and the inlet valve will be open, so air fuel mixture will come into the cylinder. So these are the five key events or processes like compression, ignition, power stroke, exhaust, and intake. And we have distinct strokes for each process. And like we have in four-stroke engines, we have four strokes. All these five processes are completed in four strokes. and 2 revolutions of the crankshaft, because I told you for one stroke the shaft rotates 180 degree, and for two stroke the shaft rotates 360 degree. This completes the one revolution. And in the second revolution the intake and exhaust take place. So in the intake and exhaust and intake processes, the exhaust and intake valves are open, so there will be no pressure buildup, so there will be no power output, so you get no power output in the second revolution. So you get power at on every second revolution of the crankshaft rotation. So now let's, if we talk about two stroke engine, in two-stroke engines, the main difference is that all these five key processes take place in two-stroke. That is why they are called two-stroke engines. And we do not have the intake valve, the exhaust valve, camshaft, rocker arm, spring mechanism, tappets. We do not find these things in the two-stroke engines because there are no valves. But uh, uh, instead of walls we have openings on the sides of the cylinder. We have openings. Now these openings are covered and uncovered with the help of movement of the piston. So as you can see here, right now this opening is covered due to the position of the piston. Now let's suppose this we are at the top dead center, and this is the power stroke. The spark plug gives the spark and the exhaust gases are formed. Then they will push the piston downward. So when the piston is going down, so this is initially it will be the power stroke. So it will be exactly similar to the four stroke engine, but the end of the power stroke will be different. As the piston goes down, when it reaches to the near to the opening, or this opening, um, when the piston comes at this position, as you can see here, this opening will be uncovered. So when this is uncovered, the exhaust gases are formed in the cylinder. These exhaust gases, because these exhaust gases will be at high pressure, so these, because of the high pressure, and outside is the atmospheric pressure, so because of the pressure difference these exhaust gases will go out of the cylinder. Now then, as it goes further downward, this opening will also be uncovered, and at the bottom, and in the crankcase part, we already have the air fuel mixture. I will tell you later from where this air fuel mixture has come. So this we have the air fuel mixture. When this opening is uncovered, then through this transfer port the air fuel mixture will come into the cylinder, and at this instant both openings will be uncovered, so air fuel mixture will come in, and we have made a hump shape like. So this air fuel mixture will go in the upward direction because of the shape of this hump. So the air fuel mixture will go in the upward direction. It will make this loop, this path, and it throws the exhaust gases out of the cylinder. This is called scavenging with the help of air fuel mixture. And then and during this scavenging process, some quantity of the air fuel mixture will be lost, and this is the drawback of the two-stroke engine, but we have to deal with it. So then the air fuel mixture will be filled in the cylinder, then the piston will go upward. This is the compression stroke. So the air fuel mixture will be compressed, spark plug will give a spark, ignition will take place, the exhaust gases will be formed, and the exhaust gases will push the piston downward. So and then the process continues. That is, the exhaust gases are formed, these exhaust gases will push the piston downward. This first, the exhaust port will be uncovered, the exhaust gases will go out, some of the exhaust gases will go out. Then as the piston goes further downward, the intake port is also uncovered, the air fuel mixture will come in. As the piston will go up from uh, from from bottom dead center to the top dead center, the air fuel mixture through this valve, non-return valve, the air fuel mixture will come into the crankcase, and this and due to the movement of the crankshaft, this air fuel mixture is slightly compressed, so its pressure will slightly increase. And when this opening is uncovered, this slightly pressurized air fuel mixture will go into the cylinder, and then when the piston goes up, this air fuel mixture is compressed. So air fuel mixture will come in when the piston is going in the upward direction, from bottom dead center to the top dead center. The air fuel mixture will come in and it will be slightly compressed. So this is the working of a two-stroke engine. Uh, so this is another figure which shows the working of the two-stroke engine. This is the exhaust port. This is the intake port, and at this moment both ports are covered, but at this moment the exhaust and intake ports are uncovered. So the air fuel mixture will come in because of the hump. It will make a path like this. The exhaust gases will be thrown out of the cylinder. This is called the scavenging process, and through this port, the air fuel mixture will come into the crankcase. Okay, so now let's discuss the comparison of four-stroke and two-stroke engines. So the main difference is that the thermodynamic cycle is completed in four strokes of the piston or in two revolutions of the crankshaft. So thus one power stroke is obtained in every two revolution of the crankshaft. This is the most important difference between two stroke and four stroke. As the name suggests, in four stroke engine we have four strokes for five processes, that is compression, ignition, power expansion, power stroke, exhaust and intake. These are the five processes, and for these five processes we have four strokes, and four strokes means two revolution of the crankshaft, and power will you will get power on every second revolution of the shaft. But in two-stroke engine we only have two strokes, and in these two strokes all the five key processes are completed, and since we only have two strokes, so it means one revolution and we will get power on every revolution of the shaft. So this is the main difference between two-stroke and four-stroke engine. Second point, because of the above, that is, we get the power on every second revolution of the shaft, turning moment is not so uniform, and hence a heavier flywheel is needed. So if you find an engine which has a heavy or a bigger flywheel, then you can say that this is a four-stroke engine. So this thing will be done in the practical viva. So you will have the practical, you will have the practical viva. So I will show you different engines, and I will ask you whether it is a two-stroke engine or four-stroke engine. So if you see valves, if you see the camshaft, if you see the rocker arms in the engine, then you should straight away say that, sir, this is the four-stroke engine. But if you do not see the valves, camshaft, but you see the ports, then you will say, sir, this is the two-stroke engine. And when, let's suppose, you see a heavier flywheel or a bigger flywheel, then you will say that this might be a four-stroke engine. And but in two-stroke engine we get the power on every second, on every revolution of the shaft. So the forces which are acting on the piston connecting rod and the crankshaft, they will be uniform. And when the forces are acting uniform, so the torque will also be uniform, and you do not need a heavier or a bigger flywheel. In four-stroke engine, forces will be acting in one revolution of the shaft, then there will be no force because there is no combustion, there is no power stroke in the second revolution of the shaft. So no force will act in one revolution. So the forces are not uniform. So when the forces are not uniform, the torque will also not be uniform. So you need a bigger flywheel. The third point, because of one power stroke for two revolution, power produced for same size of engine is less. So if you have same size of four-stroke and two-stroke engines, so two-stroke engine will produce more power, because in two-stroke engine you will be getting power on every revolution of the shaft, and but in four-stroke engine you will be getting power on every second revolution of the shaft if you compare the same size of the engine. Because of next point, because of one power stroke in two revolution, lesser cooling and lubrication requirements. So lower rates of wear and tear. So we have because forces are acting in lower magnitude, so and because combustion is not taking place in every revolution of the shaft, so cooling requirement and lubrication requirement and wear and tear, they all will be less in magnitude. But in two-stroke engine we require greater cooling, lubrication in the in the spark ignition engines. And you know that in if you those who are using the bikes, in bikes normally we have two-stroke engines, so there is a critical requirement of the oil. Let's suppose like 1 to 5. In 1 to 5, if you run like 1000 kilometers, you have to change the oil, otherwise the engine will get sealed. The next point, four-stroke engines have valves and valve actuating mechanism for opening and closing of the intake and exhaust valves. This is the main physical difference. You will find the intake and exhaust valve, the camshaft, the tappets, the spring mechanism, and the rocker arm. But in two-stroke engines, two-stroke engines have no valves, only the ports, exhaust and intake port. Because the next point, because of comparatively higher weight and complicated valve mechanism, the initial cost of the engine is more. So like it makes sense. If you have more parts, then the weight of the engine and the cost of the engine will also be higher. But in two-stroke engine, because they are simple, they are simpler, they are lighter in weight, they are less complex, they have lesser parts, so that is why two-stroke engines are less costly. Their initial cost is not that much. So if you go to buy a bike, like if you want to buy a 70 bike, cc bike, then you can buy like a very good bike like for 40-50,000, and if you go for a 0 meter bike, then you can buy like 70 or 80,000. But if you want to buy a four-stroke engine, like mostly the four-stroke engines are used in the cars, then the cars are very expensive because their engines are complex, they have more parts, so that is why they are costly and their initial cost will be higher. Volumetric efficiency, this thing we will discuss in the later part of today's lecture. Actually, volumetric efficiency is the breathing ability of the engine, that how much oxygen is going into the engine. So volumetric efficiency is more due to more time for the induction. So like you have a proper intake stroke, so you can take a good amount of oxygen into the engine. But in four and two stroke engines, you are actually doing five processes in two strokes, and there is not a special process for the intake stroke. So intake have a very less time. So when the intake is having a very less time, um, oxygen too much amount of oxygen cannot be inducted into the engine. So volumetric efficiency will be slightly lower as compared to the four-stroke engines. Actually, volumetric efficiency is showing how much oxygen, how much air is going into the engine for the combustion. Thermal efficiency is higher, part load efficiency is better for the four-stroke engine. This is because I already told you that in two-stroke engines, there is a moment where both intake and exhaust valves are open. So when the intake and exhaust valves are open, the air fuel mixture will be lost. And last week I showed you the videos. You can see that the engines are running at a very fast speed. So like within second, hundred of revolutions are taking place. So this is a very fast process. So this is not like taking place in slow motion. So like the intake will be different. Intake will be difficult, and it will be also very difficult to throw out all the exhaust gases from the two-stroke engines in the cylinder. So some exhaust gases will be left in the scavenging will cannot be taken place properly. So some exhaust gases will be left in the cylinder, and then these exhaust gases will be mixed with the air fuel mixture coming into the cylinder in the next cycle. So they will do the dilution of the air fuel mixture. That is why the efficiency or the part load efficiency of two-stroke engines are not that good. So four-stroke engines are used where efficiency is important, like that is in cars, buses, trucks, tractors, industrial engines, aeroplanes, power generation. And two-stroke engines are used where low cost, compactness, lightweight are important. For example, in mopeds, scooters, motorcycles, hand spares, small generators, lawn movers. Uh, in there you can use the two-stroke engines like the small ships, small boats, uh, and motorbikes, scooters. There, these two-stroke engines are used because they are the budget. If you have a low budget and a small scale application, then you can go for the two-stroke engine. So these are the points which we have already discussed. You can go through them, and if you have any question, you can ask in the live session or in the group. So now let's watch a video to explain all these concepts in a better way.
Let's look at the principles of the two-stroke petrol engine. The two-stroke petrol engine is different from the four-stroke petrol engine. In a two-stroke engine, the inlet and exhaust ports are opened and closed by the movement of the piston. But it is still an internal combustion engine and has the 5 events common to all such engines. Intake occurs when the air-fuel mixture enters the crankcase. It's then transferred from the crankcase to above the piston. Compression, forcing the mixture into a small volume. Ignition, when the spark from the spark plug ignites the mixture and it burns. Power, where energy released by combustion generates the force that turns the crankshaft. And exhaust, removing leftover gases. As in all internal combustion engines, these 5 events must occur, but not always in the same way. The whole process is a cycle. A new mixture enters and is ignited. Combustion occurs. Expanding gases drive the piston down and turn the crankshaft, which pushes the piston back up the cylinder.
Okay, so this was a video showing the working of a two-stroke engine. You can watch it again, and you can observe the key events which are taking place in an engine model. Okay, now let's start the last topic of today's lecture. We will be discussing different engine performance parameters. Um like the efficiency, mean effective pressure, power output, specific fuel consumption, air fuel ratio, such things. So let's talk about the input. So what is the input of an internal combustion engine? As we discussed that internal combustion engines are heat engines, so their input will be heat. So this is this block of the highest length, the maximum length is showing the input of an engine of a heat engine. So this is energy E in fuel. This unit, let's suppose kilowatt. Now this energy will be converted into, this input will be converted into output. So output is BP and IP. IP stands for indicated power and BP stands for the brake power. So you can see that the brake power box is the smallest in length, and the energy in fuel box is the largest in the length. So input is largest and the output is smaller than the input. So where this energy has gone, some energy has been lost because of the losses. Now what are these losses? So like in the first stage, energy in the fuel will be converted into indicated power, and let's suppose this is 100. So 100 kilowatt of power is supplied by burning fuel, and let's suppose 30 kilowatt of power is produced and 70 kilowatt is lost. Now this energy will be lost, like for example energy losses in exhaust, coolant and radiation. So you know that the exhaust which is coming out of the engine, its temperature is quite high, so it has some energy, and from where this energy has come, this energy has come by burning fuel. So this is the drawback of internal combustion engine, that you cannot extract all the energy, you cannot convert all the energy of the fuel by burning fuel into the useful work output. This is the principle of the heat engine, and this is the limitation of second law of thermodynamics, that you cannot convert all the heat into useful work output. So you have to reject some heat to the lower temperature body. So this is the, so some energy will be lost in the exhaust, and then you need the coolant. So because if you run the engine without coolant, so this thing, what happens, all the parts are made of metals. So thermal expansion of the metallic parts will take place, and ultimately the piston will expand, and when the piston will expand, it will be jammed, it will be blocked, it will be sealed in the cylinder, so the moving parts will not cannot move. So if you run the engine without coolant, so this is not possible, so you have to cool down the engine. So when the let's suppose from radiator water, cold water goes into the engine, it extracts heat from the engine, and this heat is the useful heat which you are getting by burning fuel. But you have to take out this heat. You have to do the cooling, otherwise the engine will get sealed. Then there are radiation losses because engine is at high temperature. So whenever there is a high temperature body, it loses heat to the surrounding with the help of radiation and convection. So these are the modes of heat transfer by which the heat is lost. So uh, for example, I'm telling you that let's suppose 100 kilowatt is produced by burning fuel. Then let's suppose 40 kilowatt will be lost in exhaust, and cooling losses and radiation losses. And then there will be further losses, and these losses are the energy losses in friction and pumping. Like, because I told you that in the internal combustion engine we have moving parts, a lot of moving parts, and whenever a part is moving, so whenever two parts are moving and rubbing against each other, there will be some energy will be produced because of the friction. Some heat will be generated, and this heat will be lost to the surrounding. So BP is the actual is the output which we are getting at the shaft, and IP, indicated power, is the power which we are getting at the piston phase. So the power comes at the piston phase, and then we have the moving parts, and then we we will there will be a further loss of the energy by the help of the frictional losses. Accordingly, we have uh, three types of efficiency. One is the indicated thermal efficiency. In the indicated thermal efficiency, you divide the indicated power with the input, that is the energy supplied by the fuel. Brake thermal power, brake thermal efficiency is the ratio of brake power divided by the energy of the fuel, and mechanical efficiency is the ratio of the brake power to the indicated power. So let's discuss more the indicated thermal efficiency. There are two definitions of thermal efficiency as applied to internal combustion engines. One is brake thermal efficiency, and the other is the indicated thermal efficiency. In brake thermal efficiency, we use the brake power, and indicated thermal efficiency, we use the indicated power. So indicated thermal efficiency is the ratio of energy in the indicated power, IP, to the input fuel energy, EF, in appropriate units. So indicated power, let's suppose it is in kilojoule per second or kilowatt. Energy in fuel per second should also be in kilojoule per second or kilowatt. So let's represent indicated by IP, and energy in fuel per second by EF. EF can also be obtained by multiplying the mass flow rate of the fuel with the calorific value. So mass flow rate of the fuel will have a unit of kilogram per second, and calorific value of the fuel has a unit of kilojoule per kilogram. So kilogram will be cancelled out, kilojoule per second. So you will get the kilojoule per second, and kilojoule per kilojoule second, they will be cancelled out, and you will have the dimensionless number, that is the indicated thermal efficiency. So let's suppose if an engine has indicated thermal efficiency of 38%. So what does it mean? It means that let's suppose if you have 100 kilojoule per second of energy or power in the by burning fuel, then out of 100, only 38% will be converted into indicated power, and rest, like the 72%, will be lost. 72, or sorry, 62% will be lost in the exhaust losses, coolant losses, and radiation losses. So this is the meaning of the indicated thermal efficiency. We will also do different numericals. We will use these parameters, and we will use these formulas. Now, what the brake thermal efficiency, as I have already told you, in brake thermal efficiency, brake thermal efficiency is the ratio of brake power to the energy in fuel per second. So let's represent the brake power with BP, and energy of the fuel with EF. And BP, energy of the fuel, can also be obtained by multiplying mass flow rate with the calorific value. And if we have brake thermal efficiency 30%, it means that out of 100 kilowatt of fuel energy, only 30% will be converted into the useful power output, and 70% will be lost. If you, let's suppose if you are buying a petrol of 100 rupees, then only the 30 rupees petrol will be converted into useful work output by, and 70% 70 rupees fuel will be lost. So actually you are dumping your 70 rupees either in the frictional losses or exhaust losses, coolant losses, and radiation losses. So this is the fact. Like the normal automobile engines have efficiency of around 30 or 35% or 25%. So this is the fact that you are actually more than 70% you are of your uh, money to the atmosphere. You are dumping this useful energy to the atmosphere. So this is the case, this is the scenario. So now it's up to you. So the engineers are always trying to improve the efficiency, so they are trying to uh, build efficient engines so that they have the higher efficiency, and higher efficiency means a better utilization of the fuel or the resources. And this, and please important, it is important to note that brake thermal efficiency is always lower than the indicated thermal efficiency, because brake thermal efficiency, brake power has greater amount of losses. So brake power will be less than, brake power will always be less than indicated power. So brake thermal efficiency will always be less than indicated thermal efficiency. So mechanical efficiency is the ratio of brake power to the indicated power, and indicated power can be written as, indicated power is actually BP plus FP, brake power plus frictional losses. So as you can see from this figure, indicated power, indicated power, let's suppose, let's represent this thing as FP, and this is BP. So BP plus FP is actually IP. And mechanical efficiency can also be written as a ratio of brake thermal efficiency to the indicated thermal efficiency. Brake thermal efficiency is BP upon EF, and indicated thermal efficiency is IP upon EF. Energy of the fuel will be cancelled out, and you will be left with BP upon IP, which is the mechanical efficiency. And what does it, let's suppose if 78% is the mechanical efficiency, it means that uh, the 32% energy is lost because of the frictional losses. This is the meaning of the mechanical efficiency. Now volumetric efficiency, as we have already discussed, that volumetric efficiency represents the breathing ability of an engine, that how much air is going into the engine. So volumetric efficiency is the ratio of actual quantity of air drawn into the cylinder to the maximum quantity of air that can be drawn into the cylinder. So let's suppose you have a cylinder, a piston cylinder device. So according to the bore and stroke of the, or the piston area, and the swept volume, according to the swept volume depends on bore and stroke. You can draw a maximum amount of, or a theoretical amount of air into the cylinder. But as I have already told you, engine is running at a very very fast speed. All the five processes are taking place like in nanoseconds. So you do not have enough time to take the enough oxygen or air into the cylinder. So uh, let's suppose 10 meter cube of oxygen can be drawn into the cylinder. This is the maximum amount of oxygen that can be drawn into the cylinder. But let's suppose in actual condition you are drawing only 8 meter cube of oxygen into the cylinder. So 8 is the actual quantity of air drawn into the cylinder. 10 is the maximum amount of air that can be drawn into the cylinder. The ratio will be 8 upon 10, or 80%. So volumetric efficiency 80% indicates that you are drawing 80% of the oxygen into the cylinder that can be drawn into the cylinder at maximum. So 100% means actual quantity of air is equal to the maximum quantity of air that can be drawn into the cylinder. So what are the formulas for the volumetric efficiency? This is a typo mistake. It should be V. I will correct it in the slides. So volumetric efficiency, it will be equal to, let's suppose, mass of air in kilogram, and this is the actual amount of air, and the theoretical or maximum amount of air can be obtained using the cylinder size. Let's suppose we have the swept volume of the cylinder. This is in meter cube. Multiply the density of air kilogram per meter cube. So meter cube will be cancelled out. You will be left with kilogram, and this will be the maximum amount of air that can be supplied to the cylinder. M dot air, that is kilogram per second mass flow rate of air. So this has a unit of meter cube. Now you need to have, sorry, this has a unit of, this has a unit of kilogram. Now you need to multiply with 1 upon second. So you can multiply with n, and what is n? N is the number of power strokes. So n can will be equal to n upon 2. N is the revolution per minute. You can convert it into, by dividing 60, you will get the RPS, revolution per second, 1 upon second. So if it is 4-stroke engine, then it will be, number of power stroke will be half of the RPM, n upon 2, and for 2-stroke engine, n will be equal to capital N. So n is the number of power strokes. So this thing we have already discussed, that in 4-stroke engines you get power stroke on every second revolution of the shaft. That is why n is equal to n upon 2. And in 2-stroke engine you get power stroke on each revolution of the shaft. That is why n is equal to capital N. Similarly, if you are given like the meter cube quantity of air in meter cube, then you can also determine the volumetric efficiency. Then it will be volume of air, actual volume of air divided by swept volume. And if you have the volume flow rate V dot air, so volume swept volume multiplied by N. These are the formulas for the volumetric efficiency. Now, relative efficiency is the ratio of thermal efficiency of an actual cycle to the ideal cycle. So we learned in the thermodynamics course as well that we have actual cycles, then we do simple assumptions like the air standard assumption, and we obtain the ideal cycles, and ideal cycles have the highest efficiency. So the ratio between actual thermal efficiency and the air standard efficiency is the relative efficiency. This is again the typo mistake. I will correct it. It should be relative efficiency. So relative efficiency of 50% means that let's suppose the air standard efficiency is, let's suppose 30. Air standard efficiency is 30 and the actual thermal efficiency is 15. So 15 divided by 30, you will get 50%, 0.5. The actual efficiency is half of the ideal efficiency. The another important parameter is the mean effective pressure. This thing we have already discussed in the course of thermodynamics, that mean effective pressure is actually the mean pressure, the average pressure, and it is a fictitious pressure that does not exist, because in the constant pressure does not exist in the engines. Because if you remember, in the real engine, in the actual engine, pressure is always changing. In compression stroke, pressure will increase. In ignition, pressure will suddenly increase. In power stroke, pressure will decrease, and when you have the exhaust stroke, the pressure will again suddenly drop. So pressure is continuously changing, but you can obtain a mean or average of this varying pressure. So this is represented by this constant line. So, and it should produce the same work output. So the area under this cycle should be equal to the area under this cycle. So then it will be the mean effective pressure. It should produce the same power output if you apply on the engine. So we can, what is the formula for the work? Force work is force into displacement. So mean effective pressure into piston area. Pressure into piston area, because pressure has a unit of force upon area. So if you multiply pressure with area, you will get force, and multiply by stroke. This is distance covered by the piston. You will get the work output, and piston area into stroke will be displacement volume. So the mean effective pressure can be obtained by dividing the work output by the swept volume or a displacement volume. So this is the formula for the mean effective pressure. And if you recall, in the course of thermodynamics, I gave you an example of let's suppose there is a batsman, and batsman has batting average. If let's suppose the batsman has an average of batting average of 52, 52 batting average. So does it mean that he has scored in each inning 52 runs? It's not because you divide the total runs by the total number of innings and you get the average number. So this is exactly the same thing in the engines. In the actual engine, the pressure is always changing, but you can take the average of this thing, the average pressure, and it is a fictitious pressure. So if you use the indicated power, then it will become indicated mean effective pressure. If you use the brake power, then it will become the brake mean effective pressure. So indicated power divided by swept volume, and swept volume should be multiplied by the number of cylinders, because it might be possible you have more than one cylinder. So swept volume should be multiplied by the number of cylinders to get the total swept volume. And since we have the indicated power, that is kilojoule per second, so you should also have a unit of per second. So we have multiplied with the n, and n is the number of power stroke. It will be equal to n by 2 for 4 stroke engines and is equal to capital N for 2 stroke engines. And why we have multiplied by 60? Because we will directly use the indicated power in kilowatt. So to bring the kilowatt to watt, we need to multiply by 1000, and then we use the n in rpm. So it's up to you that you can, like, when the data is given, you can convert kilowatt into watt, and you can convert rpm, revolution per minute, into revolution per second by dividing 60, or you can do it directly here in the formula. 1000 for the to convert kilowatt into watt, and 60 to convert rpm to rps, and swept volume will be equal to length stroke into area, piston area. The mean piston speed is a very simple thing. Mean piston speed you can get 2 L, and L is the stroke length in meter and N is the revolution per minute. And here it should always be N. It's not like this that for 4-stroke engine you will use N by 2 and for 2-stroke engine you will use simple N. The formula for the specific speed, means piston speed, is same for 4-stroke and 2-stroke engine, that is 2ln, and it is often a more appropriate parameter than crank rotational speed for correlating engine behavior as a function of speed. And the range of mean piston speed for most of the engines is 8 to 15 meter per second. Automobile engines operate at the higher end, that is, the automobile engines have 15 meter per second mean piston speed, and the large marine diesel engines which run at the lower speed has the mean piston speed of around 8 meter per second. The specific power output is the power output per unit area. The BP, if you divide the brake power is the actual power at the shaft. If you divide with the piston area, then you will get the specific power output. And then BP upon A will be equal to constant multiplied by brake mean effective pressure into specific mean piston speed. So this thing you can see from here. So if you look at this formula, BP upon N, you leave it here. BP upon area, you leave it here. Here this thing, BP upon A, you leave it here. Then L and K will be multiplied with the brake mean effective pressure, and then if you put the value of capital N, you will have Ln will be equal to specific speed, and you will have to put some constants. So specific power output will come out to be proportional to mean effective pressure or mean piston speed. So if you want to increase the power output of the engine, you can do it by either increasing the brake mean effective pressure or by increasing the mean piston speed. If you increase the mean piston speed, there will be material stresses, there will be fatigue effect or the stresses on the material, and if you increase the mean effective pressure, there will be like the more thermal load on the engine parts, because if you want to increase the pressure or the brake mean effective pressure, you need to have um, a better heat transfer in the engine. The higher amount of heat should be transferred. There should be like high temperatures in the engine, that then you will have the high pressures, and it will put load on the thermal load on the thermal stresses on the engine parts, because all the engine parts are metallic. But these are the two ways. Now you have to do a compromise, that what should be the appropriate values for the brake mean effective pressure or the mean passenger speed. The specific fuel consumption is a very important characteristics of an engine, and it reflects how good the engine performance is. It is inversely proportional to the thermal efficiency. So specific fuel consumption is fuel consumption per unit time divided by the power. So we divide the fuel flow rate by the power. So let's suppose if the specific fuel consumption is 10 gram per kilowatt hour. So it means that in order to produce 1 kilowatt hour of energy, you need to burn 10 kilogram of fuel. This is showing this thing. So the lower the specific fuel consumption, the higher will be the efficiency. If you are putting less fuel to produce 1 kilowatt hour, then this is actually showing the efficiency of an engine, and higher an efficient engine will have lower values of its specific fuel consumption. This thing, you like when you go to buy an engine, you always ask that what is the petrol average, what is the mileage of the engine, that is how much fuel will be consumed to run 1 kilometer from the vehicle. Fuel air or air fuel ratio is actually like fuel air ratio is the quantity of fuel divided by the quantity of air. It's a very simple thing, uh, because for combustion you need fuel and you need oxygen, and oxygen is readily available in air. So actually you are supplying air. You take air from the atmosphere, and this air is supplied to the fuel, uh, and then fuel takes oxygen from the air, and then the combustion takes place. So if in the mixture contains just enough air for the complete combustion of all the fuel in the mixture, then it is called chemically correct or stoichiometric fuel air ratio. So let's suppose if you need 10 gram of fuel to burn, so 10 gram of oxygen to burn all the fuel, then this is the stoichiometric fuel air ratio. So you have the exact amount of air. If you have more fuel and less air, then the chemically correct mixture, then this is the rich mixture, that is the fuel rich mixture. Fuel is rich, oxygen is less. And if the mixture contains less fuel or oxygen is more, then this is called lean mixture. So rich mixture means fuel is in excess, there is less oxygen. So when you use the rich mixture, there will be incomplete combustion, because if there is less oxygen, then all the fuel will not be burned, and then this in unburned fuel will go to the atmosphere through the exhaust gases, and then it will pollute the surrounding. So it is always a best practice to run the engine at either at a stoichiometric fuel air ratio or lean fuel air ratio. Fuel lean means oxygen is in excess. So there is a if oxygen is more, then it will make sure that all the fuel will be burned in every case. Then we have the equivalence ratio. Equivalence ratio is the ratio of actual fuel air ratio to the stoichiometric fuel air ratio. If the equivalence ratio is 1, it means actual fuel air ratio is equal to stoichiometric fuel air ratio. If equivalence ratio is greater than 1, when will be the phi greater than 1? When the actual fuel air ratio will be greater than the stoichiometric fuel air ratio. And to make this value larger, you need to have higher amounts of fuel. So then the actual fuel air ratio will become higher. And when you have excess fuel, then this is the fuel rich mixture, and the equivalence ratio is less than 1. Then it means that the actual fuel air ratio is less than the stoichiometric air fuel ratio. And to make the fuel air ratio uh, lower in quantities, then you need to put less fuel and more air. So this is the ratio now, fuel air ratio. So this thing can be asked in the MCQs, in the quizzes, assignments, or in the final paper. That what is the meaning of what is the meaning of equivalence ratio greater than 1? What is the meaning of equivalence ratio less than 1? Then we talk about the calorific value. Calorific value will tell you that how much energy will be produced by burning a unit quantity of the fuel. So let's suppose the calorific value of fuel is 1000 kilojoule per kilogram, then it means it's showing that 1000 kilojoule of energy will be produced by burning 1 kilogram of fuel. Okay, so this is all. So in today's lecture we started the lecture by discussing a few applications of internal and external combustion engines. uh, then then we discussed the two-stroke engines, a comparison between two-stroke and four-stroke engines. Then we watch a video, and then at the end we discuss few engine performance parameters. Now you have to, I request you to memorize or memorize these formulas, because these formulas and these parameters will be used in solving the numericals in the next class. So in the next class I will solve a few numericals on the basis of these formulas, and different boundary conditions, different conditions will be given, and we have to, let's suppose we need to find the brake thermal efficiency, indicator thermal efficiency, mean piston speed. So few parameters will be given and few output parameters will be required. So let's end today's lecture. See you next time. Allah Hafiz.